Alright, so in this question, we have a very sort of difficult experiment that we want to design to test a hypothesis. And so the real key to this question is understanding the hypothesis, because if you understand that, then you'll be on the right track to at least approaching the question with sort of the right topics to discuss, even if you do it maybe in the slightly wrong way. So we're going to look at that first, then we'll start designing the actual experiment. The hypothesis is this. It's the last line of that sort of introductory paragraph. The student hypothesizes that the collisions are very close to being perfectly elastic for low-speed collisions, but they are more different from perfectly elastic the faster and faster you collide. So to interpret that, we need to remember that elastic collisions mean energy conserved, right? That's the key, right? So the hypothesis can be sort of restated as if the ball collides with something at low speeds, energy is conserved. If the ball collides with things at high speeds, energy is not conserved. That's his hypothesis. That's a much more clear statement of what's going on, but you have to understand and remember that relationship. So let's get to the experiment with that in mind. So we're trying to compare low and high speed collisions, and we want to do something with energy. So first thing to think is, what are we going to measure if we want to measure an energy? Right? Because if we want to test this hypothesis, we have to measure energy somehow. That way we can see if it's conserved. So there's two different ways that I can think of we can do that. We could measure a height, right, mgh, or we could measure a speed. Technically as well, you could do something involving like throwing it at a spring, and then you can measure the spring compression length. But I think that's a little bit bizarre of a thing to assume, right? You could do it, but I'm not going to discuss that one. Really, I think height and speed are the two logical ones. So let's say, I'm going to write in blue for this. Let's say we determine we're going to measure a height. So we need to do an experiment that tests different speeds of collisions, and we need to measure a height after it. Right? That's the idea. So what I would do is I would drop the ball, since I know equal, right? If we drop a ball from rest, the higher we drop it, the longer it falls, and the faster it travels. So I would place the ball at different heights above the ground, actually I should be consistent with which h I'm using, and then record that, drop the ball, and then record height it bounces to. Right? Oops, that's the wrong two. And this is terrible handwriting actually, so let's just start over. Right? If we did something like that, we'd measure the energy before and after the collision. That would test the energy conservation part. Good. If we did this, we also have different velocities that we hit the ground at, so different speed velocities. So we'll test if energy is conserved as you change the speed you make a collision at, which is good. That's what we need to do. So this procedure would address the hypothesis. What about the speed one? So this one we need to somehow, I guess I should clarify, what equipment would be used. This would be like a meter stick, right? You're measuring an actual height. You probably need to be a little bit more detailed than I've been here too, but I don't want to handwrite it all. I've been talking about a lot more. This is the big structure. Alright, so speed. How would we do that? Well, if we want to measure a speed instead of a height, we can't measure it quite as easily, but we could still do it. So this one, we might need something like a motion detector a photo gate. Right, those are two things we used in our lab setups to measure speed. And so we could do something like throw the ball or drop ball. At different speeds. Either through photo gate or in front of the motion detector, right? Either way. Record the speed and then have it sort of bounce back through and record the speed again. Right, or bounces back towards the motion detector and record the speed again, whatever that might be, something like that. And again, I'm being brief because I don't want to write on the iPad screen, but that's the general idea. And the key is, right, to specify different speeds, just like different heights right there. And those two experiments, I think the height one is a little bit easier to actually implement in a lab setting, but both of those experiments will record the energy before and after collisions as you change the speed the collision happens at, right? And so that will, roughly speaking, answer the question. Right, you'd also need to say something in there somewhere like, since we need this mass, we need to put the ball on a scale and record a mass, right, if we want the energy before and after specifically. Okay? Alright, so now we have a question where we need to figure out how we're going to show this data. And there are a lot of different ways that you can do this. I think the simplest, I'm going to use the bounce height first. Simplest is to plot H final versus H initial. Or you could make this mg H final, or it doesn't matter because the mass of the ball and G doesn't change. You can either plot the height or mgh for the energy. And then if you plot these data points, right, you're going to see them kind of scattered around, something like that, maybe, who knows. But if the slope is about 1, then that means that HF is about equal to HI and energy conserved. Right, so our analysis would be look at the slope. If slope is less than 1, then that means HF is less than HI and energy not conserved. You can do the same exact analysis if we did it with, instead of H's, if we did it with VI squared and VF squared, right? That's the kinetic energy. It'd be the same sort of slope analysis. There's another graph you could do too. You could, because this doesn't make it clear unless you remember, that this data point came from low V. Well, actually, no, it does make it clear, right? And you know that the points down here are low velocity because they're small height, so small velocity and so on, and then points up here are high velocity. There's another way you could plot this. You could plot, right, as a function of like the impact speed, you could plot a ratio on the other axis, HI over HF, or you could plot VI squared over VF squared, right, if you did the other one. And so if you did this, when that ratio is about 1, so this is like 1 here, like that. And so what we'd expect to see is that if the collision is elastic, then the value of this is somewhere around 1, maybe a little bit less. Right? So like maybe we get a data point like there, make it a little bit clearer, like there and there and there. And then if it gets more inelastic, then the denominator gets bigger and the numerator gets larger. So it would be something like this. And so if we have like this, if value, actually that's all right, if the ratio is about 1, then energy, I hate writing on iPads, conserved. And then here, if ratio less than 1, then energy not conserved. Right? You could also, instead of a ratio, you could do a subtraction. Right, so I'm going to go to gauge. So you could also do something like HF minus HI and VF squared minus VI squared versus V impact. And so here, we're actually going to have potentially negative numbers. Right? If we have energy conservation, these are going to be roughly the same value. And if we don't have energy conservation, then we're going to get negative numbers, right? Something kind of like that. Oops, I want to use blue. So to conclude from this one, we'd have if difference is about 0, then energy conserved. And if difference less than 0, then energy not conserved. Right? So one thing to note is that if you choose either of these second two approaches, you're going to have to show how you calculate that impact velocity, right? That's not either of these initial velocities. Or sorry, yeah. At least potentially, depends where you put the photo gate. So you might need to do an extra calculation if you want one of these graphs. Right, so any of those three will work, right? Either a plot of one versus the other, a ratio, or a difference. All three can be concluded from. But you have to be clear exactly sort of what I wrote. What shows that energy is conserved? What shows that energy is not conserved? Exactly what are you plotting? What's it going to look like? All of that. Alright, so here, now that we've kind of started, I'm only going to do one graph for this. I'm going to do the ratios of the heights one. And so the student does this experiment, and they get some data, and they get a graph, and they realize that something has gone wrong. So their graph is going to be HF over HI, so we'll call this 1, as a function of the impact. Right? So energy is conserved if we're right around that area. And so the student concludes that the graph shows this, that the collision is elastic for low-speed collision. So that means we have data that's kind of like that. That's what we concluded before. But for high-speed collisions, violates a basic physics principle. So you notice that in all those previous graphs, we never had an occasion. We had occasions where energy was lost, but that's because energy can't be created out of nothing. So a basic physics principle to violate here is anything that sort of creates energy, or right, if HF is greater than HI, that's a problem. So for this graph, that's a ratio greater than 1 means energy created. So that would be something like showing for high-speed collisions we get like this sort of data. Right? That would be reasonable data that would fit the description that was given. For low-speed collisions, we're about at a value, a ratio of 1, so it's elastic. And then for high-speed collisions, the ratio is bigger than 1. We've created energy from nothing. Right? And you can similarly see how all the other graphs would be modified to violate this sort of energy conservation thing. I'm not going to do all of them this time. So now we actually need to discuss it. Well, what do we do? Well, kind of what I just said, right? for the correct description of the aspect, well, if ratio greater than 1, actually I'm going to rewrite it, right? The correct description of what the violation is that this is what shows it, right? If the ratio is bigger than 1, that tells us energy is created. And it's because the final height is bigger than the initial height. It bounced higher than we dropped it from. Right? The final energy is greater than the initial energy. So something like that would work. Right? And so that's it. And I think this one's especially hard because of the difficulty of understanding the hypothesis, right? There's a lot going on in that. But if you take the time to look at the hypothesis carefully and connect sort of those words to physics concepts you're used to, then the problem becomes much more approachable.